I think I can start my lecture. So today we are going to talk about spherical coordinate system. Spherical coordinate system. So in this spherical coordinate system, instead of using what is that x, y, z Cartesian system, we are again going to use another coordinate variables like r, phi, and theta. R, phi, and theta coordinates. Okay, so what are r, phi, and theta coordinates? I have to keep clicking admit all. So as you can see here, this is I think you can see that there is a point P here. We can consider, what happened to my pen? Yeah, there's a point P over here. So consider a point P over here. The location of this point P can be defined using what is your XYZ coordinate system. So you can again use your XYZ Cartesian system, and using the like by knowing the value of the X coordinates, Y coordinates, and Z coordinates, then you would know the location of the point, or in other words, the location of the point is defined. And another way of locating this point P or defining the position of this point P is to use this coordinate system called spherical polar coordinate system, coordinate system, in which instead of using our XYZ system, we are going to use R, phi, and theta. Okay, so here in this case, your u1 will be r, your u2 will be phi, your u3 will be theta. So what is r here? R is simply a measure of distance of the point P, a measure of distance of the point P from the origin. A measure of distance of the point P from the origin is called r. Right, the distance of this point from this origin to this distance is called r. And by the definition of this R, I think you will know that now what will be the range of R here. In order to cover every point in the space, the range of R will have to go from, like if you are at the origin, the range of R will be 0. The value of R is 0. Like if you want to define the location of any point in the space, you should be able to extend your R value till plus infinity. So from this, you can see that R variable can vary from 0 to infinity to cover every point in the space. Like if you have another point here, for example, point Q, if you want to know the location of this point in this coordinate system, first you have to find out what is the distance of the point from the origin. That is called your R here. So at the origin, R value is 0. As you move along, you can extend up to positive infinity so that you can cover any point in the space. And now let us getting back to this particular point P here. If you drop a perpendicular here, and you can see that there is a line from the origin to this perpendicular, and the angle it subtends, this line, the angle it subtends with respect to x-axis is called your phi coordinates. This is another coordinate variable called phi coordinate variable. So depending on your phi value, if you move your phi from just a minute. Just a minute. a little bit interruption. Just one more. I'm so sorry. Oh, Mesa. 900 mm chu polycap khani me ya engkhung ek to lo mo kalak chu shme nga. Oh. Fan dimension ka. Oh, fan ni ka se ka. Fan ka ron ti lo mi. Join a chu ma kha ding lo mi a blade lo mi. Ka mu to na. Oh. Ka khalo ka petel lo oh thuna ka hong nam to lo task force duty le police belt om throka dor ko la ke no china ko ka request ka hong from ma na tu lo ma ron ti me to ka ti pon goi nan te chat ai chu lo man jing lo ma khan lam ve me tur ne ya da so pa ni thleng chau dor hon tu ni la ya chu lo ma hon je ka du lo mo kami a clip te kha o perak var te kha chu lom ti ran soi lok sa lo wa nak tu la man mani po nak tu ka ro to men ka ti fen chu chi to lo trim duty nom thama mo an kal ka du to lo ai chu nom chat wa okay sum dong ni jona boi thak deu ni this one moment. So now I think by now you will realize that phi is the angle its subtends with respect to x-axis, and in order to cover any point within the space three-dimensional space here, your phi has to vary from 0 to 2 pi. So phi can vary from 0 to 2 pi. With that, you can trace out every point on the first quadrant, second quadrant, third quadrant, fourth quadrant. You can trace out any point here. Now, what about your theta coordinate here? Theta coordinate line, as you see, it is simply the angle, this R line, R coordinate line, the angle R coordinate line subtends with the z-axis. Theta is the angle it subtends with the z-axis. So if you vary theta from, let's say, 0 to pi, if you vary from theta from 0 to pi upon 2, then you are able to cover only the top half. If you want to go beyond the top half, like if you want to extend to the lower half, theta can go from 0 to pi. Theta can go from 0 to pi. Okay, theta can go from 0 to pi. Now, theta can go from 0 to pi. The reason why I'm not extending theta from 0 to 2 pi is that why I'm not extending from 0 to 2 pi is that if I extend up to 2 pi, it would be a little bit redundant. So, like for example, at this particular equation here, if you extend your theta value from 0 to pi here, you are able to cover the top side, the top half that is above the xy plane. This is, you see, this is the xy plane, above the xy plane as well as below the xy plane. Now, if you vary your phi around this circle here, if you vary your phi around this circle here, you are moving away you are moving this point along this circle. So even for a particular theta value, if you vary your phi here up to this point, for example, you are able to locate this point, isn't it? So what's on the back side also can be located if you vary your phi from 0 to 2 pi like this. Because as you vary your phi from 0 to 2 pi, this point will move along this circle like this with the same value of r, and with the same value of theta. So there is no need to extend theta value from beyond pi here. if you extend up to 2 pi, this is simply redundant because you are able to cover any point over here, any point over here, if you move your phi from 0 to 2 pi. So the theta value extends from 0 to pi only. The theta value extends from 0 to pi only. Okay. So you can just picture it yourself also. Now, here, this is your R here. This line is your R. Now, if this is theta here, what will be this line? This will be your R sine theta. Now, this is parallel with that. So, this is your R sine theta. Let me redraw it. I think that will be more convenient, easier to understand, I hope. Something like this. So let me redraw it here so that you can have a proper visualization of what we are talking about. So this is your x-axis, this is your y-axis, and this is your z-axis. So let's say we have any arbitrary point P here. So using spherical polar coordinates, we can define it using r, phi, and theta. So what is r? This is the origin. From the origin, you measure the distance of this point P, that is called your r. And if you drop a perpendicular on the plane of this xy, this is the line, and this the angle it subtends with the z-axis is your theta, and someone is not muting herself or himself. So the angle it subtends with z-axis is theta. So this will be your r sine theta, and similarly this will be your r sine theta. Now the angle this line subtends with the x-axis is your phi. So if you drop a perpendicular here, this is your corresponding x coordinate. So your x coordinate value will be this itself is r sine theta. So this will be your r sine theta cos phi. This angle is phi, remember that. Okay. So if you draw a perpendicular here, this is your corresponding y coordinate here. So this y coordinate will be r sine theta sine phi. Okay. R sine theta sine phi. So this, when you write x coordinate variable in terms of this r sine theta cos phi and y coordinate variable in terms of r sine theta sine phi, and what is your z coordinate variable here? The for this particular point, the corresponding z coordinate variable is this. Z coordinate value is this. So z will be, this angle is theta, so this will be r cos theta. Z will be your r cos theta. So this relation is called the transformation relation between the polar coordinates, sorry, spherical coordinate system and Cartesian coordinate system. And you know that if you take x square plus y square. So I once again request everyone to mute themselves, and I don't think I should admit any more students after this, because as and when they join, they are inadvertently unmuting themselves. It disturbs the class. So if you take x square plus y square here, this will be your r square sine square theta, and this is cos square phi plus sine square phi, and this will be your r square sine square theta. This is cos square phi plus sine square phi is 1. So this is your x square plus y square. And if you again add another z square here, if you take z square, this will be r square cos square theta. So if you add all of this, x square plus y square plus z square will be r square. Sine square theta plus cos square theta is 1. So the reverse transformation relation, you can obtain it by writing r as x square square root of x square plus y square plus z square. And if you follow such things, you can write this as your reverse transformation relation. And here, as I was saying, y is r sine theta sine phi, x is, yeah, over here I have already written here, this is x, sorry, this is x, there's a typing mistake. So x is this, y is this. Then if you take the ratio of y upon x will be r sine theta sine phi r sine theta cos phi. This and this will cancel out, then you will get your tan phi to be equal to y upon x, and then you can write your phi coordinate variable in terms of the coordinate variables of your Cartesian system, y and x. That is the transformation relation between phi and xyz coordinate system. And similar to that, you can also obtain your theta as this. Your theta, it can be expressed as tan inverse of square root of x square plus y square upon z. Okay, and this is what I have already discussed. The range of these coordinate variables are like this. Now, once you know this transformation relation, that is x is r sine theta cos phi, y is r sine theta sine phi, z is r cos theta, you can write your position vector. So the position vector, as we know, we can write it as xi plus yj plus zk. And by putting the value of x as this, by putting the value of y as this and z as this, this is the position vector in your spherical polar coordinate system. So once you have this position vector, you can obtain your unit vector. What will be the first unit vector here? Tangential unit vector er cap. Instead of your e1 cap, now we have er cap. Er cap will be position vector differentiation with r coordinate and divided with the magnitude. Like this, you can get the e1 er cap. Or the second unit vector, tangential unit vector, will be e phi, which you can obtain it by differentiating the unit vector with the phi coordinate variable and dividing it with the magnitude of that. And the third unit vector, e3 cap, instead of e3 cap, we will now have e theta cap. E theta cap will be del r vector upon del theta upon del r vector upon del theta magnitude. Like that, once you have this transformation relation, you can write the position vector. Once you have the position vector expression, you can obtain all the unit vectors. So here, this magnitude is called your HR, the scale factor. Instead of H1, now we have HR. And this is your scale factor H phi. This is your scale factor H theta. So everything is written here. So you just differentiate it, take the magnitude of that. How do you take the magnitude of a vector quantity? You take a square root and take the square, sum the square of each and every term here. Okay. So with that, sum the square of each and every term, then you are able to get the scale factor. So if you follow this calculation, I think this is just trigonometry. You are taking a common factor here, and sine square plus cosine square is 1. Then you will find that your first scale factor HR is 1 here. The second scale factor H theta is R. The third scale factor H phi is R sine theta. H phi is R sine theta. Okay. Now, what are the coordinate lines here? What are the coordinate lines here? Let me go back to this picture again. So the coordinate line, the first coordinate variable is R here. The coordinate variable corresponding, the coordinate line corresponding to R variable is, as you see, it can go from 0 to infinity. So our coordinate line is a straight line. Our coordinate line will be a straight line. It goes from 0 to infinity. It is just a measure of the distance of the point P from the origin. And what about your phi coordinate line? Phi coordinate line, as I have discussed, phi variable, it can go from phi equal to 0 to phi equal to 0 to 2 pi. So let's say we start with the point P here. We start with some certain point here. Over there, your phi value is 0. Now, if you move along this and if you arrive at this point, your phi value become 90 degree. And if you move around that, behind this, your phi value will become 180. And then eventually, when it comes back to this point, your phi value become 2 pi. So